Hello everyone, and in this video we're going to be looking at the first two questions of AS 2023 statistics for Edexcel. And we've got a histogram question to start us off. So it says a histogram and its frequency polygon below give information about the weights in grams of 50 plums. Okay. Show that an estimate for the mean weight of the 50 plums is 63.72 grams. Now, the first thing I should notice is it can be a little bit confusing about what's the connection between a frequency polygon and a histogram. Now, when you have a histogram where all of the bars are of equal width, as you can see we've got in this question, and you connect all of the midpoints of the tops of the bars, that is a frequency polygon. Okay, so in A-level, if they ask you, for example, to draw a frequency polygon from a histogram, what you're going to be looking for is a histogram where all the bars are of equal width, okay, and you would connect the tops. So that's just a little point of reference. Now we've got to find an estimate for the mean. So let's have a look. First of all, we may remember that the mean x bar is equal to sigma fx over sigma f, okay? So that's our formula for calculating the mean. So we could do with knowing the frequency and we could do with knowing the midpoints, okay? So we're going to need to calculate all of those. So let's make this a little bit bigger so we can see clearly for our calculations. So let's have a table. We're going to have MP for midpoint and we're going to have F for frequency. So midpoint and frequency. So our first midpoint is 61. Now, what's the frequency associated? So remember, in a histogram, the frequency is given by the area underneath the bar, okay? So we've got to find the area of this. So we can see it's 2 wide and it's 3 high. So it's going to be 2 times 3, and that is going to be a frequency of 6. The next one, midpoint is 63. What is going on with this bar? It is 2 wide and it is 12 high. So it is 2 times 12. So it is equal to 24. There we go. Next one is 65 is our midpoint. We can see that it's 2 wide and it is 8 high. So it has a frequency of 16. And then finally, we've got 67 as the midpoint, which is 2 wide and 2 high. So therefore, a frequency of 4. Okay, so now we're in a position to calculate our sigma fx. Okay, so sigma fx is going to equal 61 times 6 plus 63 times 24 plus 65 times by 16 plus 4 times by 67. Okay, so that's our sigma fx, and all of that has got to be divided by sigma f, which there are 50 plums, okay, and that is going to give us our mean, sigma fx over sigma f. And when we calculate that, lo and behold, we put that into our calculator, it does indeed turn out to be 63.72. So that's part A done, okay. Yeah, let's see what's next. Part A. Now, calculate an estimate for the standard deviation of the plums. Right, so let's go back to our table, because in order to find our standard deviation, the standard deviation is equal to the square root of sigma fx squared over sigma f minus x bar squared. So you may hear one of those little things where teachers say sometimes that the standard deviation is the square root of the square of the mean minus the mean of the squares. Okay, so it is basically we've got to do the mean of the squares rather minus the square of the mean. So let me say that again. So standard deviation is the mean of the squares minus the square of the mean square rooted. Okay, so in other words, we've got sigma fx squared minus the x bar squared. So we need now to calculate what is f times by x squared. Okay, now remember that these midpoints, they are our x values, as it were. This is one point where students commonly make a mistake, actually, because what sometimes students do is they kind of would go 6 times by 61 and then square the whole thing. Or I've seen students square the 6 and then times that by 61, okay? But what it actually is the frequency times by the midpoint, the 61 squared. So we need 6 times by the 61 squared, okay? And then we need 24 times by 63 squared. And then we need 16 times by 65 squared. And then we need 4 times by 67 squared, okay? So that's what we need to be working out there. So let's have a look at that. So for our sigma fx squared, what we're going to have is sigma fx squared is when we're going to add all of those together, okay? And that's going to be over sigma f minus x bar squared. We're going to be square rooting that whole thing for our standard deviation. So what we need is we need to work out 6 times by 61 squared plus 24 times by 63 squared plus 16 times by 65 squared plus 4 times by 67 squared all over 50 plums added together minus our mean squared, and our mean was 63.72. 63.72 squared, the square root of that whole thing. And when we pop that into our calculator to calculate our standard deviation, the standard deviation turns out to be 1.58216. So let's give it to, say, 3 significant figures. 1.587. Oh, it's the square root. Sorry, let's have a look. It is going to be, let me get that number right. So the standard deviation is actually 1.58795. Sorry about that. So when we round that up to 3 significant figures, it's going to be 1.59. So there we go. That's our standard deviation, 1.59. Good. Now, what's going on? Later, it was discovered that the scales used to weigh the plums were in fact broken. Okay. Each plum actually weighs 5 grams less than originally thought. State the effect that this will have on the estimate of the standard deviation from part B, giving a reason for your answer. Well, let's have a little think about that. So here we have, now, I know we don't know about this distribution AS, but this is, let's say, a normal, this is a normal distribution. It's just a representation of how the plums might be distributed. So the plums have a standard deviation like, let's say, like that. So the standard deviation measures how spread out the data is. Now, if every single plum happens to weigh 5 grams less than was originally thought, okay, then all that means is the whole distribution is just moved 5 grams to the left, but it's still exactly the same shape, okay? In other words, crucially, the plums are still exactly at the same distribution in terms of how spread out they are. So the standard deviation is unaffected, okay? There is going to be no change to the standard deviation at all, because all of the plums were 5 grams heavier than thought. So the distribution of them remains the same. Perfect. Right, let's have a look at the next question. Now, in this next question, what have we got? So let's have a look. I'm going to bring across this one from over here. Okay, so here's another version of the same question. So what have we got? It says Fred and Nadine are investigating whether or not there is a linear relationship between the daily mean pressure in hectopascals and the daily mean air temperature in Beijing in 2015 using the large data set. Okay, Fred randomly selects 1 month from the data set and draws a scatter diagram in figure 1 using the data from that month. The scale has been left off the horizontal axis. Okay. Now, describe the correlation shown in figure 1. Well, basically that data, it's really hard to tell. I mean, I think that you could either say that there is no correlation, or you could say that it is a weak negative. Okay, so for that one, we would either say no correlation, okay, or you could say that it is a weak negative. But I think I would go with no correlation there because it's really hard to tell. That's part A. Now, Nadine chooses to use all of the data for Beijing in 2015 and draws a scatter diagram for figure 2. She uses the same scales as Fred. Okay, now we can see that we've got a negative correlation going on here. Explain in context what Nadine can infer about the relationship between P and T using the information shown in figure 2. Well, I think that Nadine can conclude that there is a negative correlation. If I just bring up this here where we can see somebody's written the answers down, we can see that there is a negative correlation, okay? Because as the mean pressure increases, the mean air temperature decreases, okay? So we're going to say that there is a negative correlation there. Good. Now let's have a look at the next bit that we're going to do in this question. So the next bit, what have we got here? It says, oh, here we go now, using your knowledge of the large data set. Wow. Using your knowledge of the large data set, explain why it is not meaningful. Oh no, actually I've forgotten part C. Using your knowledge of the large data set, it says, state a value of P for which interpolation can be used with figure 2 to predict a value of T. So in essence, what they're kind of looking at here is for us to understand from the large data set, what's like a kind of range of values of pressures. Well, in the large data set, the pressures are going to be ranging from somewhere around about 990 all the way up to about 1040 hectopascals. Okay, so that's like our sort of range. So really, if you kind of put any value in there, it would be appropriate. And we can see that we've put here, it is 1010 hectopascals, but they'll accept anything in between 990 and 1040. But because that's like the range of values, you want to go somewhere in the middle of that. But again, that's just purely a knowledge recall from the large data set. And then finally, it says, and this is I've seen this come up a few times, using your knowledge of the large data set, explain why it is not meaningful to look for a linear relationship between the daily mean wind speed using the Beaufort conversion and the daily mean air temperature in Beijing. So in other words, why can we not compare these two things? Well, the Beaufort or Beaufort, I'm not sure how you pronounce it, conversion is what we call it's a qualitative data, okay? So it's things like we have, like, say, for example, light winds, or we have, you know, strong winds and so on. So that is qualitative data, not quantitative, okay? We can't measure it. It's not a wind speed, you know, measured in sort of like miles per hour gusts or anything like that. It is just qualitative data, light, medium, and so, you know, and so on. Where, however, the air pressure is what we call quantitative data because it's got a number associated with it. So you can't compare qualitative data with quantitative data. It'd be like trying to compare somebody's eye color with the length of their hair. It's kind of like not really meaningful, okay? So we've got written here, in the large data set, the daily mean wind speed using the Beaufort conversion is a discrete scale of qualitative data. In other words, it's discrete because either you've got light winds or you've got strong winds. It's just certain values, yeah? Whereas the daily mean air temperature is continuous. It can be anything, and it is quantitative. So it is not meaningful to look for a linear relationship between those two things because one is discrete and qualitative, the other is continuous and quantitative. So we can't really be comparing them. Perfect. Well, I hope that you found that helpful. And that is the first two questions on AS 2023 statistics.